Hey everyone, hope you're doing well. Welcome to another Isaac Sim Office Hours session. In today's session, we'll be focusing on the robot import process and all the variety of importers which you can use, setting up physics and walking through that whole process. And we have Renato from the Isaac Sim team as well to help us out here. So over to you, Renato.
Hi, hello everyone. I don't know. I've been here once before, so I don't know who of you know me. I am Renato. I am one of the Isaac Sim engineers. I've been here for a while. So welcome to everyone that is here interested in this talk. What I am going to show you today, I want to go through the very basics of setting up a robot on Isaac Sim. Some of the things are going to be repetitive for many of you, but I think it is important to level everyone on the understanding. And even though there's things that are very basic, let's call it that way, there's always some nugget of information that you can get out of whatever I show today. So stay in, let's see how that goes. And as we progress, you can keep asking questions. I can adjust whatever I'm showing to that. So yeah, let's go. So I have just get a fresh install of Isaac Sim 2023.1.1. So this is the first time I'm actually opening this version here. Of course, I have my development branch that is elsewhere, but I wanted to go from the very basics, from the very beginning of whenever you have your setup installed. One thing that I did extra was install my Nucleus local host. I'm going to be using this later today. For now, the first thing that I wanted to show is, okay, so you open this up, you want to start simulating things. What do you do? First thing is, let's click play. Okay, now you're simulating, great, but what's happening? Nothing. Oh, well, let's create something here. Let's start by setting up some basic things on the simulation. First thing is one rigid body. This is going to be like the body of your robot. The first thing you have to do is add. I went through this a little bit fast, so let's go back again. I went on create mesh cube, and that generated this for me. I just zoomed out because it was very big. Actually, if you see my grid, if you can see it, it is a 1 by 1 meter grid. So this cube is actually a whole meter. Let's actually scale this down a little bit. Let's make this 40 centimeters by 40 centimeters by 40 centimeters. And now it is actually floating on top of the grid. So let's move this down a little bit, 1, 2, and we have our cube here. And again, nothing happens because this is just a static mesh. To make this a rigid body is something that you're going to simulate on. Click on Add, Physics, and Rigid Body with Collectors preset. What this does is make this an actual physics-enabled attribute, physics-enabled asset on your scene. So now when we hit play, this is actually going to fall. There we go. And it's falling because we don't have a ground plane. Next thing, let's create a ground plane. And I know this is, for many of you, this is all old news, but I wanted to go from the beginning. And now we have a ground plane here. Doesn't fall anymore. And we can actually play with this. We can either, by selecting it and moving around, we can move its position, and it's going to simulate that. Another way that you can interact with scenes here is if you shift and left click on the object, it creates this drag that you can pull things around and test, like what is happening, what goes on. There are some attributes that you can work on this for physics. If you scroll down here in properties, you scroll all the way, there's going to be a physics tab that contains a rigid body that says other things that you can try, even here, set a linear velocity. So like 10 meters up is actually going to make it jump. And even though it doesn't update it here now, if you go in and out of the scene, it should update that. So yeah, now it is stabilized in 0, so it doesn't change anymore. Same thing for angular velocity. It fades away very quickly because it is touching the ground. So yeah, but a single body is not something that you want to simulate most of the time. You want this to be a robot. Let's start with something like a mobile base. So we're gonna have this body and just 2 basic wheels on the sides of it. So let's create our meshes for that. And this is gonna be, let's do actually mesh. No, I don't want the shape. Let's do cylinder. Great, we have our thing here. Now we want to make this smaller, 20 centimeters. Yeah, I think that's fine. And we can always rotate things here. So one thing, we can always try to rotate it directly here. So like 90 degrees like this. But let's say that we want something different. We want, like from this position, we want to make it at a different orientation. So there's a problem here that when we try to rotate like on Z, it doesn't move anymore because now our axis is actually here. So if we want to rotate this around the actual Z offset here, we can click on this offset mode and add a 90 degrees here. That should rotate it correctly. So, and I did this because I want my robot face to be on the x-axis here. So now I can drag this around and I can place this close to my robot body. Let's zoom in. Now there's always a parallax issue here that things are not exactly aligned the way you want. So we can move things around. I can always resort back to numbers here. So I want it to be at 0. So now it is aligned at the center. And let's make it a 0.15. No, actually 2. 2 here. That is clipping inside of my thing. So 0.435. Okay, that's good enough. And then this one, 0.215, so it is slightly, no, I want this to be closer to ground, something like this. And yeah, it's gonna fall whenever I run simulation here, but well, let's add physics rigid with collider preset, and let's create a new one for the other wheel. So this is gonna be a minus 0.3. And this will be the shape of our robot. And now let's, if I try to simulate this now, let's create rigid bodies, physics. Actually, I think I have to do this one by one. Physics. Or did I already make the rigid body for this? Oh, I did. Okay. So yeah, if I try to simulate things now, yeah, things are not really connected. So the next thing we need to do is actually create the joints between the robot. So we select our main body and our cylinder and go to not Isaac, create physics joint, and then a revolute joint. And this is interesting here. You see that we have this circle around our joint, and that tells us what is the axis that it's rotating around. And in this case, it is on these x-axis here. So we want to scroll down and change this to z. So now it should rotate in the same direction as the cylinder. And let's do the same thing for the other one. Create physics joint revolute joint. I think there's another way to do this. If you go on this, right click here, create physics. It's essentially the same menu, but on top of what you're doing. Now, if you scroll down here, set it to Z. Okay, so now we should have something that stays in place. Yeah, you can see that robot is kind of there doing something. Let's do some inspection to see what are the properties that we have on those bodies. So to do that, we can come on Window, Simulation, Physics Alternate Toolbar. And then here we can do this mass distribution manipulator. So now when we select things, it actually shows us what is the total mass of things and what is the diagonal inertia and even the principal axis. So this blue outline here is our inertia. We can actually manipulate it through here. We can make it like move it around, or we can scale it with this small. There's a few things that you can do here. This gizmo, there's a lot of things going on here. So yeah, you can scale the inertia, change it somehow. I actually want this to stay fixed. So, but by the time I did this, it automatically created for me mass properties here. So I can always reset this back to 0 so that my inertia doesn't change. I want this to stay similar to like a cylinder would be. Okay, so next thing is actually how do we control this robot? And for that, we need to add a joint drive on this. So physics. So we select our joints here, and then add physics angular drive. And there's two main ways that we can control this. One is by position, another one is by target velocity. And since this is a mobile base, it doesn't make much sense to do a target position because the wheels would spin for a while and then it would stop at a given angle, and that doesn't really translate much on how we usually control bases. So we are going to use target velocity for this. And the way that this works is we have a stiffness parameter that tracks the difference between our target position and our current position. So because we want this to be velocity controlled, we set the stiffness to 0. And damping is the same thing for target velocities. So we want to control this target velocity, so we set this damping to something greater than 0. So in my case, I'm going to do 1000. So let's do this here. And then if I set a damping of 300, let's see what happens here. And the robot moves. Cool. So let's understand what is happening here. So if we look at the joints here, both joints are aligned in the same direction. So whenever I set a target velocity, it starts spinning forward and makes the robot go in the direction we want. If we set one joint to 300 and the other to negative, naturally it should spin. Yeah. And yeah, this is the most basic version of a robot that one could create on the simulation. So yeah. Now, there's one more thing that we can do to make sure that our simulation runs smoothly, and this is usually how we set up all the robots. Not only having basic joints like this, there is an extra API in physics that gives more stability for the simulation. And to do that, you select your main body of your robot and click on Add, Physics, Articulation Roots. This is actually necessary for the Isaac Core APIs. I'm not going to go into that today. So whenever you want to start coding using the Core API, this is going to be important. But in essence, it doesn't really change much on the simulation. It just makes it more stable. So yeah, here we are. And this is cool. This is fun. Setting up this robot like this. We had some benefits of having the joints aligned. So uh, whenever we created this, it already gave us the joints in the position that we wanted. But imagine that we want something that is not really properly aligned like this. So let's say I have something that is going to spin on top of the robot here. So let's create a new body to do that. So a new cube. This is going to be like a 0.3. No, actually 0.1, 10 centimeters. And I didn't do this, but you can always toggle this link scale. So whenever you change one, it changes everything. 2, for example. And then you can move this around. And I want this to be, imagine that, for example, this would be like a camera that is sitting on top of the robot, and you can actuate where you want this camera uh, to look at. And I want my joint to be where those two bodies connect. So when I come here and click on those two cubes, this one and this, and add my physics joint, it creates a joint in the middle of this body. So let's go and do the same thing we did before. Set it to the, actually this time it's going to be on the y-axis. But now if I try to simulate this, this body is going to, oh, something happened. It didn't work the way I was intending. So world cube 1. Oh, I know. I forgot to set this as a rigid body. Okay, cool. So now it is there. But you see, it is not rotating where we want. It is actually sitting in the middle of this. So you can come here and you can drag this around and try to set it where you want. And you can always go on this local position 1 and 0 and set it manually. So that would be a 0.5, 0.5, minus 0.5, minus 0.5. That would be on where we want it. And I didn't set up the drive, but I think you get the idea of this, right? So let's go here, add joint drive. And this time, this is going to be a position based. So we can set stiffness to 1000, damping to 100. And now this is going to stay in place. Cool. And I mentioned we want this to be a camera, so we could always come here on this cube, create camera, and then place it inside of the cube. And now, if we were to look at this, so now you can see that if I change this, the camera is actually going to move along with that. So if I move this up or down, the camera is going to be pointing down now. And I think it's actually giving me the other direction of things. Where is it? Yeah. Yeah, it is actually showing me the robot face. It is taking a selfie. So yeah. I can always revert this camera and make it look on the other direction. Actually, would this be this one? Okay, I think this one, yeah. Let's look at the perspective. Okay, yeah, now it's looking forward, and you can bring this back. So yeah, but this is fun. You can make this robot yourself, but most of the times you already have like a CAD file or a URDF that you want to import. And luckily, we do have options for that. So we can always, instead of building a robot like this from scratch, we can always come here on Isaac Utils, Workflows, URDF importer, for example. And from here, you can always import any URDF file that you have. We have a collection of samples that are shipped with IsaacSim that you can try out. They are going to be on this built-in URDF files, which goes to a folder on your install file. And then we have robots here. And the robot that I will import for us in this case is this Kaya robot that is similar to ours, just a mobile base. And we have some import options that we can set here. So we can set all the drives to position, none or velocity, and then it will use this information for the drive strength, depending on this. And this is going to be for all joints. We are working on this to make this per joint setup so that you can update things. And you're going to see why this is important as soon as I finish importing this. Other things that you can work on is the kinds of collisions that are going to be here. And if you want this to be administrable, we can go on this in the future. So yeah, and then when you click on import, it's actually going to ask you, okay, it's going to be saved on this folder. Yes, because I didn't select a folder here. I could always change a directory. So let's actually go on my documents and put this here. So now it imports there, and my Kaya is here. Then when I hit play, oh, something happened. Why? Oh, this is one thing I forgot. There's a fixed base link. This is our mobile base, so we don't want this to be fixed. It is an easy fix. You can always come here, delete this root joint, and then now robot moves as expected. And you can drag this around or try to, and it should move, hopefully. This does not want to move. It is trying, but it is taking some effort. So let's take a look at all the joints of this robot and see what happened here. So we have our axle joints. Those are the joints that are being controlled by the robot. And we have a target position, target velocity here. And damping is set to 1,000 or a million, I don't know, 10 billions maybe. So I could always try to setting the velocities to those. But we can always go into the joints. This is a fixed joint, but here on the wheel 0, that has all these small roller joints for the Kaya, those are all set to a damping as well. And those are really non-actuated joints, so we don't want this to be there. We want this to be like a 0.01 just for some stability. And we have to do this on all joints. So we could set this to none on the importer if we had a per joint basis. So this is going to come soon so that we don't have to do this post-processing here. Okay. Are there any questions that I can take on as I do this?
Yep, I think we had a question from Dawood asking that if we can command force or torque to the actuators instead of position and velocity. So
Yes, there is. There is a force. It is called effort command, not through the UI. So today I'm doing the most like interacting and making sure that you set up your scene and the robot kind of works on the UI. But when you go into code, there is apply joint efforts instead of set target velocity or set the target position. So with that one, you can actually go directly into joint efforts. And the difference is essentially that the target position and velocity takes this as a gain, like a pretty much like a proportional gain tuning for velocity and position, converts it into an effort, and then applies to the joint in the simulation. When you apply the effort directly, you can set up whatever you want there. So it is just a matter of like those are going to be set to 0, and then you add an extra effort on top of that for the joint. And there's one thing that is important to note here. There are 2 ways of applying the effort on the joint. One is by force, and the other one is through acceleration. And the difference here is the acceleration one, it doesn't take the bodies into account. So it doesn't take the masses of the robot. It just directly applies velocity, acceleration inputs, or how do you call that, impulses, acceleration impulses on the simulation time step for that joint. So it automatically gives the right velocity, updated velocity for that. But if you have a force type, it actually takes the mass into account, computes the acceleration, and then applies an acceleration to it. Because it is an acceleration-based control, according to how the simulation works. So it always reverts back to that. So yeah, if you want to go directly on forces, it is going to take that into account. And then if you actually should go over here, it says that in max force. And this force is the same one as the type 1 above. So if it is a force, it's going to use mass times distance units by second. And if it's an angular drive, it is distance units squared, because it actually takes into account the torque that is generated as well. And if you change it to acceleration type, it just takes the mass out of the equation there. So that's it. But that's a good question. Okay, so now if I hit play here, I can, let me filter by joints here, because I want to find all my axle joints. Axle joints. And I can set this to a target velocity, let's say 200, and the robot should move. Yes, there we go. And then there's always OmniWheel controller that you can set up so that it actually moves forward, set one axle to one direction and the other to the other direction, so that it actually moves forward, ignore the last one, whatever. We do offer this controller, this holonomic controller that can set up for Kaya, but that is a topic for another day, I think. But yeah, URDF is fun. You can always import this from here, but you do require the URDF for that. So if you don't have a URDF, you have a CAD file, what do? There are some options too. So you can go here from import, and this takes step files, AutoCAD, everything. Downside of this is step files, CATIA files, any CAD files in general, they do not hold joint information. So all that authoring that I did on this manual robot that we implemented, that needs to be done. And that's one of the reasons why I wanted to go through that process from the beginning. So whenever you import your robot, you know how to create the joints, you know where the menus are. All of that can be done programmatically as well. We expose those APIs. So yeah. And alternative for that is importing from something like a known shape. And I'm going to go into more specific topics when we go from there, because I know that this is something that always shows up on questions is, okay, we have this linear robot, like this actuator, and it's great to have this 6-off arm, but it's a basic structure, and that works fine. But when I try adding loops to this, things break. So how do we go around fixing those? So what I'm going to do is I'm going to show you one asset that has those, and that is set. And that is actually going to jump into this question from Navid. Is there a free lib of pre-made robots? We do offer some robots with our shipping of Isaac Sim. So if you install your Nucleus, you can come to this NVIDIA folder. You're going to find it. Or let me clear the scene here. We don't need this URDF importer for now. I'll create a ground plane again. We have on Isaac examples, import robots. There's a few that we import from URDF. Or if we come on create Isaac, we have a bunch of sensors. We have some end effectors. We have the robots here. This is our list of robots. So the Denso Cobota 300, 900, and 1300, a Dovbot, Fanuc, some Festo, Franca. There's a few. So, for example, we can bring this Franca here. And when you click on this, it actually comes on this NVIDIA folder and imports that for you. So, and you can see that from this link here in the stage. So you notice how there is this orange arrow on top of Franca. That means that this asset is coming from a new external source file that contains the Franca definition. And if you come here in references, that gives you that asset path. So Omniverse, localhost, NVIDIA assets, and then Isaac, our current version, robots Franca. So essentially this folder here, assets, Isaac, and then we have all the versions here. Latest ones are the most up-to-date and tuned for current, so try to keep on that. Isaac, and then we have some environments, some materials, some props, and the robots. And then on this set of robots, the Franca one is on this Franca folder here. So yeah, when we click on play here, we have the robot there, and it's already set up and ready to go. And this you can always interact with the Python API. There's a list of core examples for that. But what I wanted to go into is actually this robotic hand here, the 2F140. So we have a few examples of those. The one that I'm going to focus on is this. And let's zoom in this hand. One thing I'll do is I want this hand to play nicely on my scene. So if I click play here, it is actually loose, it is open, it is ready to be connected to a robot. But for now, what I'll do is I'll just put it on a set of simple meshes that will work as a robot for us, just like we did before. So we're gonna have this cube here. It's gonna be like a 0.1 by 0.1, and I'm gonna make it. Oh, okay. Actually, I want this to be a tall tower. And we're going to have another cube. And this, actually, I want it to be a small one. And I didn't go into this, so this is actually a good opportunity for us to make a linear joint, prismatic joint. So we may come here, create physics rigid body with colliders. Let's make this our articulation root, physics articulation root. And then now we select our two bodies, create physics joint. And then we were always using this revolute joint. Let's use a prismatic joint. There's a few more. There's more than just a prismatic and revolute. You can always go there and make your choice on many different types of joints. There's a D6. Fixed is essentially blowing it into place. Spherical is 3 degrees of freedom, all rotational. A distance joint, it is saying how far apart you want the objects to be. So this would be something like a spring in between bodies that are setting them apart, something like that. Gear joint and rack and pinion are specializations of the other joints that add a relation between them. Okay, so now we have our prismatic joint here. Let's set it to the z-axis now, and I want it to have a limit. So it's going to be from 0 to 1 meter, because that is how tall our thing go. Okay, so now let's get this guy here and connect it here. We can move this around, pick the main body for our hand, and pick our prismatic joint and create a physics fixed joint. So this should actually make our hand be connected to our gantry here. Oh, I didn't fix it in place. Interesting, I forgot about that. Cool, it's always fun to see things break in simulation and figure out what we want to do there. Why is my simulation not responding? Oh well, things crash sometimes. I didn't get any error messages, but for some reason it's freezing. So I guess, should I force quit? Should I wait? I'll just force quit and come back. It's not too hard to get that back. Okay, that is a good moment to check for more questions.
I think we had general questions in the chat about how you can control your robot, what sort of are there any guides or tools in terms of understanding how you can bring your robot in, how you can set up sensors and all of that. So hopefully I've
Yes.
answered that well enough. But yeah, if
Yes,
there's anything you want to add, go ahead.
we do have on the documentation, almost everything that I'm showing here is on our documents, on like how to get started, and then there's going to be like the modes of control that you can have on the robot. One is all this UI interaction that I'm doing that does really not scale well for robotics applications. It is more like a setup. Getting things ready, preparing, making sure that the asset works as intended, doing like a sort of, let's call it unit testing of the asset to make sure that things, like it's not the asset that is breaking the simulation, it's something else. Whenever you're running things and things don't work. So this UI, I would say it is important for this like first step, making sure that everything works as expected. And then once you're done with this, you have the asset. Now you can create extensions that you can run through this UI, create buttons that import things on, makes like set things up. So let me actually start sharing my screen. I can show what I mean by this sort of extension workflow. And if things are too small or too big, or you wish I had more screen real estate space, just let me know. I can always scale things up and down. Okay, so what I mean is, for example, in this Isaac examples here, we always have things like sensors, manipulation. I'm gonna go with this one that is interesting. Everything is interesting, but I want something that is interesting to the context of what we're doing so far. I think probably simple stack is one. So it is it's a robot that stacks 2 cubes. So it's a Franca robot that we have all this control of like loading the scene here, resetting the scene, and beginning stacking. And you can always do, this is what we call an extension workflow. You create an extension that can be reloaded, and every time that things are working, like every time that your extension is reloaded, it resets things, and you can start things from the beginning again. It is good for this kind of quick development of a behavior or something that you want. So now I have it loaded. I can click on start stacking. It's going to get my robot and find the cubes and control that. And as you can see here on this overview, if you press this open in IDE button, it's going to be one of those open source code, a link to docs. Yeah, you have the full documentation here. The open in IDE, I think it is open source code one. So when you click that, it opens for me. You can see because I'm only sharing the exact same window, but I can always change my share here. Let's see. Stop screen, share screen, window, simple stack. So it shows, yeah, it opens this screen with the code, simple stack extension that lives in a folder and has the base code. So we have this base simple extension that has a fundamental method called on startup. This is what begins the entire UI development and things. So you have the different buttons on screen that you can control. And if you go on this simple stack task, that is this other one here, this is where you set up the scene, and then you do a post load thing, what happens on every simulation step, and then Yeah, this is stacking controller. It lives somewhere else. It is the base sample code for that. You can always navigate into it. So Franca controller stacking. So you will need to go on yes, Franca. That lives in a different folder, but you can always navigate to that. This is all Python code is findable on the ISAXM installation, so you can always find that and look into it. Yeah. Is there a way to post a link in the comments? I think that is very likely blocked for various reasons, and you might know why. Is the same as suitable for training a machine learning model? Yes, it is. It is made for reinforcement learning. There is the reinforcement learning stack. This is not something that we're going to be talking about today, but there are documents about that.
I think, yeah, adding to the machine learning question which we had, like you can, if you're using like deep learning based applications where you're
Yes.
maybe needing synthetic data, so you can leverage OV replicator, which is a part of
Mhm.
ISAXM, and you can generate
Yeah.
all the annotated data from there, which will contain like 2D, 3D bounding boxes, depth images, segmentation masks, all of that. So you can get all of that information out from simulation. But for
Mhm.
training the model itself, you'll have to leverage your own workflows, which you might be having. Like you could be having a PyTorch or TensorFlow based framework where you've written like the entire code to train the model. Or for example, if you want to leverage Tau, which we have from NVIDIA as well, like the Tau toolkit, that will just allow you to sort of seamlessly connect your synthetically generated data into a model, and you don't need to write anything yourself. And the output will be like a trained model, which you could then use. So you can generate synthetic data from sim, you can do RL with sim. For training, you've got various options depending on what you might be wanting to look at. And you can use NVIDIA tools, or you can use your own stuff there too. So I hope that answers the deep learning and general AI related question.
Yeah, and I think the other question was related to this: is can we use it without a ROS bridge, Isaac Gym directly from Python? Yes, we can actually run the entire Isaac Sim directly from Python. There is a Python pipeline for running the code. You can create a script that loads up the Isaac Sim application, and then you can interact with it, control your step rate, do your own step and everything, just so you would do with Isaac Gym. Another question that I saw here is about the UR5, UR3. Actually, we do have them. So if you look here on Create Isaac, you have UR3, 5, 10, 3E, 5E. So you can actually use those directly. You don't have to hack around the UR10. Is there an NVIDIA Omniverse tool available online that we might use if our GPU doesn't support app on our computer? We are working on that to have a cloud service for Isaac Sim, so that you can run on something like a Docker, AWS. I think there's some other pipelines going along with that. So yeah. XARM and XARM Lite from your factory. I am not aware of that. Never seen those before. If they have an import file, we can always import it and tune it. Most of those robots, they come from URDF, but we always have CAD files. The robotic hand that I was working on before, it actually had, it comes from a step file that, because I didn't want to deal with axis positioning on Isaac Sim, we understand that moving those arrows around, it is not a precise mechanism for placing joints. I actually imported it on shape that allows us to bring all the joints together. And actually, this is what I wanted to do on going forward, because there are some things that needs to be done in post-processing when a model is complex, like have kinematic loops and things like that, that we need to take into account. So let's actually try to get back on that. I'm going to go with the cubes that I was creating before. So 1, 2, this is going to be a port 1. Port 1. It's going to be a tower. So yeah, this question about the closed kinematic chains, yes, we do support them. That gripper hand, it actually has a few kinematic loops. It is articulation sets, they do not support it natively, but we have it working by some. It's not a trick. It is just like setting up the asset in a way that the physics understands and knows how to handle those. So essentially, we reduce the kinematic loop into a kinematic tree, and then the loop is a best effort matching. It does match most of the time, but if there's any error, it's going to be accumulated on that external link that is connecting the loop back together. So ideally, you have a kinematic tree path forward that is the one that you want, and then this one joint is the one that ties things together, but it is the one that is going to accumulate the most error. So let's have this guy.
Are you not sharing a screen if you
Oh,
were doing something? Yeah, I
thanks
figured
for
you were
letting me
doing
know. I was
something.
like, oh, yeah. I was just rebuilding the tower that we had before.
Sounds good.
Yeah. So I was in the process. Now I have this all together here. I didn't create the joints. Let me actually start by fixing this in place. I don't want this toppling over anymore. Create physics joint fixed. Okay. Now go in this, create physics joint. This is a prismatic, and it's going to be on Z from 0 to 1. And I'm gonna add a physics linear drive that adds 10,000, 100,000, and some damping just so it doesn't bounce over every time we try to move things around. So 1,000 is probably good enough. And if I try to simulate that, things are staying in place. I can move things around. Cool. So now next step is actually bringing my gripper hand again. And that was in localhost NVIDIA assets Isaac robotic. Oh, not the FC2, D140. That's the one. So, and it's not liking that hand. Things are crashing when I try to import that hand. The interesting thing is the hand works sometimes and then it crashes for some reason. Let me see. What was the error that I'm getting here? It's an obscure error about CUDA context manager, memory failed. Am I? What is happening? Yeah, my memory is free. It says I'm using very little out of my thing. Interesting. I do have some other builds running. Oh, that explains a lot. I was actually running the other version of Sim that I was developing on the back end. Examples for four-wheel differential drive robots. No, we don't have any examples for that. I know that there is some issues with four-wheel differential drive robots because they are a skid steering model, And these contact, like the friction model that allows this to work correctly, is sometimes not very well represented in our physics engine. So this is something that we already brought up with the physics engine team, and hopefully we have a solution for that in the future. But
I
for
think
now,
another
yeah.
sorry, another good question which we have from Wolfson is that how do you know that the damping and the strength of the wheels for your robot is being set correctly? Like,
You would need to track the target positions and how it reaches that pose. We can do some small experiments on that. Let's see. Share screen. Hopefully now things don't break anymore. I was actually running Isaac Sim twice on the computer, and sometimes that can create some issues with uh, memory allocation on the GPU. Okay, I'll start with actually dragging. Oops, wrong folder. Isaac, Isaac, robots. I'll start dragging this and actually go over some of the things that I mentioned about this hand. Where is robotic? Down, down, down. Okay, here we have the hand. Now it is not breaking anymore. So we can actually take a look at where the joints are for this. Let's see here. If you click on the eye, show by purpose, type, physics, joints, it creates this tiny, tiny blue things where joints are. Let me see if I can look at the top here. Can you guys see those small icons here for the joints? They are so small. Can I make them bigger? Gizmos, viewport, manipulate and transform. No, not this one. I thought there was one thing that raised that. But yeah, in any case, there are some tiny things that shows where the joints are, and if I try to click on those, can I select them and show? Yeah, okay. So here we see, and now you can probably see all the things, and we have one loop that comes from this joint to this joint, this back at this one, so it connects this body here, and there's a second loop here. So I know that this robot is actuated, this hand, we call it robot because in essence, everything that can be actuated is to a degree a robot. But even this is just a gripper. But I know that this gripper is controlled by motors that actuate this joint here and this joint here. So those need to be on like what I like to call the critical path of my actuator. So those need to stay there. And then it will move forward to those joints on the side, and then to those joints here. And this is my principal path that actuates on this soft hand, this parallel gripper. And then it moves to this joint that connects everything together and back to this one. And this is a joint that I don't really care much if it is gonna break. So what I do to enable this to work with what we call articulations is if I scroll down on the joint properties, there is this property called exclude from articulation. And what it does is it removes this joint from the articulation pathway for the physics, and it simulates this joint as a simple joint. Remember in the beginning when I was talking about it and I mentioned that the articulation pathway is a more precise method for determining the joint positionings? That's exactly that. So when I remove this from articulation, that joint is going to go through the standard joint path, which allows it to accumulate more error. So by removing this from the articulation, the joint still simulates, it still tracks and tries to achieve the position, But if the simulation constraints are breaking, this is the joint that is going to accumulate the most error out of everything. How realistic can the results look like? We can actually grip things of about 2 kilograms or more with this hand without shaking. I'm not entirely sure the published version is properly tuned. I know that we did a lot of tuning on this asset, but I don't remember if it was prior to releasing the 2023.1.1 or if it was after. So we can try picking things up and see how it looks. And that's why I wanted to build the tower, so that we go and pick things up and try to do some testing here to show a little bit of this setting up the robot and tuning the joints pipeline as we go forward. Yeah, we are actually reaching the hour though, so I don't know if it is something that we can follow up on the next section, or Rishab, how do you feel about that?
I think it's up to us. Like, what do you think in terms of you wanting to cover
Mm,
stuff right now for the gripper? There anything else you want to look at, or you want to answer a few questions? I think we had like the damping and the stiffness question. Like, how do you realize that it's the correct value? So maybe
right,
a quick
yes.
overview of that. That would be nice.
Okay, yes, I do have some extra 15 minutes. After that, I have a hard stop, so I can try going a little bit on the damping thing, and we can go over tuning the particular asset afterwards. Is tuning done internally at NVIDIA, or can we tune our own robotic systems? Yes, you can definitely tune your own robotic systems. It is a matter of importing and looking at the joint gains and working on that. For this, I think this hand is kind of there's a lot of setup to get this tested because it is not a standalone asset. It does require assembling this into a robot or whatever. So I will actually, to answer the question about tuning, either get something like a mobile base like Odin, or Franka robot. I think Franka is probably a good alternative here. Open with new edit layer. Don't save this. Create edit layer. I'm going to create this here. Customers edit. Okay, so we have this here. Let me change those slides because I like to see what I'm doing. So when we hit play here, we see that the robot goes into position, and we can track here physics joints. We can go up. There's a like we don't have a mechanism built in for this. What we do is essentially collect the data and match it, but a visual inspection is always a first step on seeing how things are going. So let's say I'll stop this, and I'll start with a simple joint here. Let's remove this damping and add some stiffness here. Then let's say that we want this to be in a target position, and we can change this position, like give it an impulse or step function, and see how it performs to that. So let's see at 30 degrees. So now we see that it's actually wobbling. It is not stabilizing the position at all. We can actually, there is one other thing that we can add here. Physics, joint state, angular. So now we can actually read the position and see how closely it is matching our target. So let's set it to 0. So we see that it's actually like hovering around and stopping. Eventually it stops at 0. So let's set it to 30. You see that, yeah, it's bouncing a lot. So that means our damping is not high enough. We can increase that. And this can follow the same methodology that a PAT tuning is done. You can always like do a step response function, analyze the how fast it is reaching the target and how much it overshoots. I anticipate that most of the times it's not going to overshoot by too much. If you have a damping that is greater than 0, this is a stable system. The way that it's implemented, it's very unlikely that you're going to enter into resonant motions or the control theory side of things where the robot is going to become unstable. So you can add some small damping here. One, 1/10. Let's see if we go to 0 now. Still bounces a lot, so 10. 30. Okay, so now it did move very nicely into position. It's stabilizing very close, a margin of error of 0.005. That looks good enough. Next step is checking how fast it's actually going into that. And for this, we do have some sort of UIs that give us a plot. We can always implement our own. Remember when I was talking about creating an extension? This is a perfect example of an extension that could be created, like a gains tuner plot view that gives you the step response. That you can always have buttons that say, "Give me the step," and it moves there. Does the damping and stiffness still have the same effect if you're using joints driven by torque force instead of position? No, damping and stiffness will have zero effect if you are. Actually, no, it will have. The effort doesn't override. It actually complements the changes on damping and stiffness. So if you have a higher than zero stiffness and higher than zero damping, as you try to apply effort, that damping will actually try, not the damping, the stiffness will try to drive your joint back to the position that is set as target. And the damping will always try to match the velocity. So even you can see what happens here. I have some damping. If I add some velocity, some target velocity here, like 60, it will actually try to set a velocity, but then because I have a positive velocity, it is moving in that position. Eventually, the position error becomes greater and it overrides the damping gain, the velocity gain. So it stabilizes at a position that is not the target position and is not the target velocity, but eventually gets to 0. So when you have a position control, it is always good to have the target velocity at 0, unless you intend to move it on a given velocity. So you can always set target position and velocity at the same time. Have some tracking that whenever it reaches that position, you set the target velocity back to 0 or something like this. It's always a way of controlling the robot. I would say this is a pretty advanced way of controlling the robot from what we've seen so far. It's probably better to implement your own torque force effort controller if you get into this kind of use case. Yeah. Does that answer the questions about tuning? Is there anything else that you want me to go into this? And I think we can make a makeup session for the second part of importing a robot with importing from CAD, like loading up a CAD file, loading up from Onshape, seeing how to set up joints from Onshape, and then from there, what is the post-processing that is done after things are imported from this kind of files? Just like there is some post-processing to be done when it imports from URDF most of the time, there's always going to be some things that we need to set up manually after importing from some of the CAD files.
Yep, makes sense. I think this is certainly good for now, Renato. And like you said, that the other topics which are still pending, like from the CAD import and the other things, we can take a look at that next.
Yeah. So for seeing the oscillations, I think the best option here would be this inspect physics that we have on the Isaac utils. That does give us the plots for positions or angular velocities and so on. For that, the only downside is you need to have the body that you want to inspect selected. So for example, imagine that we want to inspect this body 1 here, that is the one that is going to rotate right above the joint 0 link that we were playing with. So what I would do here in this case is set up a target and then start simulation. Okay, so actually let's set up a 0 target again. Make it here, and then we select this. Actually, we pause simulation, we come here, 30, It is, yeah, it's not a perfect system. There's definitely room for improvement here, but something like this, and this should give us the, yeah. For some reason, it is not getting. Oh, I was first selecting the wrong body. Oh no, that's why. Okay, joint one. Let's set it back to 0. Link one. Hopefully now, yeah, now we get some, yeah, and then here we see the response on the angular velocity, and then it doesn't stop when we pause. So yeah, there's a few things that could always be better, but we can at least see some sort of plot. Alternatively, you can always have all these transforms being reported with some through ROS, collect a ROS bag and plot this elsewhere, or make an extension that collects this information and generates the plot as well. Bridge is part of SXM. It comes with it when you import it, when you install it. So if you go on, where is that, window extensions, you get the ROS bridge here. If you right now we need to source ROS2 before loading up IsaacSim. If you do that, the extension that is going to be available here is going to be the Isaac ROS2 bridge instead. So it automatically understands if you have ROS2 sourced and enables that extension.
Yep, I think we've also answered most of the questions in the chat. So I
So
think
yeah,
we
I think we're good for now. I can definitely do a V2 for next week, go over what we missed so far, and hope to see you guys again.
thank you so much, Renato. It was great to have you here. And thanks guys for the questions. I know a couple of the questions did have more context in terms of like particular stages and headless stuff
Yeah,
related to IMU. So please post them on the forums. We're active there too, and we'll
yeah.
try to unblock you as soon as
And
possible.
I understand that many of the things that I showed today were very basic, and many of you might already know some of them. It's just that I want to make sure that we're bringing everyone on board. So yeah.
All right. Thank you so much, guys. Have a good one.